Hello, my name is Armands Kviesis and I'm from Latvian University of Life Sciences and Technologies. And today I would like to speak about honeybee colony state detection by temperature data. And at first I would like to tell some words about a scientific project that this study was carried out within. So it's called SAMS and it enhances an international cooperation of information technologies and sustainable agriculture between European countries and some developing countries like Indonesia and Ethiopia. So basically, the SAMS proposes an implementation of precision beekeeping that would allow active monitoring and remote sensing of bee colonies and help the beekeepers to manage their bee colonies. So here you can see also some keywords that is related to the SAMS project, but today I would like to touch two of them. It would be data processing and decision support systems. So if we talk about honeybee colony states, then during the whole year we can observe various states like brood rearing, swarming, colony deaths, and others. But it is possible to detect such states, like in this table that summarizes the colony states and the type of measurements that we can take. We can see that temperature, with temperature we can recognize the majority of them. And why it is that? It's because the bees are excellent at thermoregulation with heating and cooling. And so basically, if there are some abnormalities, this should be reflected in the temperature data, and we could observe that. And also, temperature sensors are quite relatively cheap, and the signal is easy to read using any kind of microcontroller. If you talk about the experiment that was carried out, it was located in Latvia, and we collected the data before this SAMS project within a different project related to bees, where we monitored 10 bee colonies and we measured only temperature. So we placed one temperature sensor within the hive above the brood frames. And the data were collected using such a monitoring systems architecture. So basically we had one Raspberry Pi device, it's a single board computer, and we used one wire temperature sensors, so multiple sensors was connected with one data line. And the data were forwarded to our remote database every 1 minute. So, and after data were collected, we started to look at the temperature curves, and so we noticed that we can quite easily, I would say, detect the start of the brood rearing. So as in this chart on the left, we can see that the temperature is about 30 degrees, and then it slowly increases till it reaches 35. On the right side, you can see some temperature curves during the swarming period. So when the bees are warming up their flight muscles, the temperature increases inside the hive, and after the takeoff, the temperature decreases. And this is like a 20-minute period. On this slide, you can see death of a colony, so the temperature slowly decreased, and it had the same pattern as the outside temperature, and at the end it completely overlapped. But on the right side you can see how beekeepers, I would say, manual weighting impacts the situation within the hive. So basically the beekeepers were placing the hives on scale, and the bees, as you can see, had stress, and so the temperature increased and the recovery period were quite long. So this clearly shows the importance of of a need for a remote monitoring system that should minimize the manual inspections causing such stress situations. And yes, also after we observed the curves, the temperature patterns, so we started to think about the concept, how we could automatically detect that. And so we need an inference system that could detect the first early stage of some abnormalities or some colony states, and then we also need some additional processing blocks that could further analyze if the correct temperature pattern is matched. So for the inference system, fuzzy logic was used. So basically fuzzy logic is a standard generalization of the standard logic. If the standard logic deals with values that are 0 or 1, then fuzzy logic takes values between those 0 and 1 and are quite similar to how humans reasons. Yes, and on the right side you can see an architecture of the fuzzy inference system that basically uses 4 main blocks: the fuzzification, that takes the input values and fuzzifies that, and the fuzzification looks like, for example, if we take in temperature as an input parameter like 35, then the fuzzification could transform it into values like very high, for example. And then the knowledge base or rule base is where experts define specific rules in an if-then format. For example, we can say if the temperature inside the hive is high, then there's something wrong with the colony, for example. Then there is this inference engine block that basically deals with the reasoning, and after that, then the fuzzification transforms the fuzzy set into a crisp output value that we can use later. And here are the input values. We used 5 inputs and one output that could be the state. For example, this, some extreme state or normal. And on the right side, you can see these inputs and their membership functions. And this slide shows you the example of those rule sets that I was talking about. So here you can see, for example, if the temperature difference between outside and inside the hive temperature is large and it is autumn, for example, then there's something wrong with the colony, for example. You can say that the state is extreme. And after the design was made of the fuzzy inference system, we trained it and tested, and here you can see some of the results that all swarming cases were detected. So whereas the temperature increased, then the system shows the assessment of the colony is like number 50, like 50%, so something is wrong. Also, abnormalities were detected during the winter period, and we are not quite sure what caused such temperature spikes during the winter period. But as we can see, the fuzzy inference system detected such situations. And also the death of a colony was also recognized. And after performing the evaluation of this system, you can say that it was quite robust and stable and showed a very high value. And as I mentioned, that there were, from the fuzzy, there were 3 states, and one of them was extreme. So basically, we don't, it's a state that we don't know exactly what is the state. And because there might be some temperature increases, but not every temperature increase would be a swarming. So then we need additional processing to like detect if the pattern of the increased temperature is the same as for swarming. Therefore, two neural networks, two models were developed. One was based on the time series data, and the other was on statistical measures with 4 inputs of the swarming curve. And here you can see the architectures. And yeah, after the performance evaluation, you can see that the model that used the 4 statistical measures as input parameters performed a little bit better than the first one. And another thing that I would like to point out is the importance of the measurement interval. So basically, when we set up a measurement system, we need to know what exactly we want to measure and what exactly we want to detect. Because if it's for swarming, for example, if we take the measurement every 20 minutes, we can miss this event. Because as we can see, there's only one point of a quite high temperature value, but it could be as well as just a linear line. So yeah, it's very important what we want to detect. For swarming, I would say 1 minute and 5 minutes is enough, maybe also 10 minutes, as we can see that we can pretty much miss this event. Yeah, and so some conclusions. Yeah, the performance evaluation of the fuzzy inference system showed that it's quite stable and can detect some abnormalities and other states in an early stage. And it can be used as a core block for a decision support system that could give some notifications to the beekeeper, who can then act accordingly to maintain his colonies. And of course, more data is needed with the ground truth, so we can know what kind of temperature pattern is reflecting the actual state. And yes, about the measurement intervals, yeah, we need to know what we want to detect, what we want to measure, and then we can change the measurement intervals. That can also improve the battery life for the measurement systems if we use battery powered solutions. And also I'd like to touch a bit to the monitoring systems that we developed during the SAMS project. One of it is based on a Wi-Fi microchip. So we designed a custom PCB and programmed it to work in a very energy efficient way to measure temperature, humidity, and weight. And it's still being tested in Indonesia, and we are monitoring Apis cerana, which is a much smaller bee colony than Apis mellifera. And so there are some of the challenges that we are facing here. It's a reliable network connection. So the colonies are placed in forests and mountain areas, and so the network connection is not always as stable as we want it to be. Also, the quality of the beehives is of much of importance, so that if we are monitoring the temperature, so the temperature won't be ventilated if it's not built from quality materials. And also, yeah, a very remote areas. So basically, if we want to maintain the monitoring system, it could take quite a while for the engineer to travel to the actual location. And here you can see examples of data from the Indonesia, where our colleagues put in 3 sensors, 2 on the sides inside the hive and 1 in the middle. And as we can see, the one that's in the middle is one of the important ones, because on the sides those values are quite the same as the outside temperature. So this also shows how it's important where the sensor is placed. Yes, and again, so this study was carried out within the SAMS project. And thank you.